Hello everyone, and welcome to the third day of our TWIND summer school. I hope you are all well. This morning we start with a session dedicated to control, and we have one keynote speaker followed by three short presentations. The way we'll do it this morning is slightly different than the previous days. We'll take the Q&A for the keynote right after the keynote talk. So please, as usual, do post your questions on the Q&A tab, which is on the bottom right of your screen, and we will address them to Jan-Willem directly after his talk. So I'm very pleased to welcome Professor Jan-Willem van Wingerden as keynote speaker in this summer school on control. And he will talk about, so he's a full professor on wind farm control at TU Delft, and he will talk about smart wind farms. Jan-Willem, you should be able to share your screen. You should also unmute yourself. Yeah, we can see your slides well.
And now you should also be able to hear me.
And we hear you well, yeah.
Excellent. So thank you, Axel. Thank you, organization committee, for inviting me, for giving this presentation. So today I will talk about smart wind farms, and I will explain smart. I will explain smart from a control point of view. So wind farms, if you talk about, let me try to make sure that I can control my slides. Wind farms, if you talk about wind farms, there is no better way of starting your talk by showing this photograph. This photograph taken by Christian Steines in 2008, a photo taken under special atmospheric conditions. And what you nicely can see in this photograph is that there is interaction between turbines, so wake interaction. So a turbine, and I hope you can see my mouse, standing in the wake of another turbine will experience a higher structural loading due to a higher turbulence intensity, and will not extract the same amount of energy as a turbine standing in the free wake. So when I talk about smart wind farms, I'm talking about wind farms that can reduce the effect of wakes. And you can do that in multiple ways. So that's going to be the main topic of today's talk. So how to reduce wake interaction. So first, let's talk a little bit about the technologies that we have. So the handles that we can control. From a control point of view, it's also a little bit broader than only wind farms. If you look at that, then we have a full technology landscape. The first one is the so-called smart rotor control. So work I also have done during my own PhD. And what that means is that every turbine will get additional degrees of freedom. And from a control point of view, it's just additional actuators. So in this slide, you see a rotor equipped with trailing edge flaps. So with these flaps, you can, for instance, do load control to mitigate the effect on partial wake overlap, for instance. The other technology is LiDAR. Probably everybody is familiar with LiDARs. From a control point of view, it's just additional sensors. So you get more information of what's going on, so you can also anticipate better. Then we have floating, which I believe is the main topic of this workshop this week. And I will also place it in perspective for a wind farm, for smart wind farms. But from a control point of view, why are floating turbines so interesting? Because of the dynamics. I mean, if you install a baseline controller on a floating turbine, it will become unstable in the above rated region. So it's really interesting to study the dynamics, and maybe you can do more with it if you look at wind farms. Wind farms, why it's interesting from a control point of view? Because of the scale and the nonlinear dynamics and the time varying conditions, and you name it. And of course, there are multiple other technologies you can also look into. The point I would like to make with this slide is that these are technologies, and it's also the interfacing with the controller. And the controller is basically saying what an actuator should do. And the controller is using sensor information. So in the case of smart rotor, you can think about distributed control algorithms. In the case of LiDAR, you can think about feed-forward control. In the case of wind farms, you really can think about distributed estimation, distributed control. But what I also believe is that if you develop control algorithms for wind turbine applications, wind farm applications, you really have to tailor these algorithms towards the application and really use properties of the system when you design your control. And we also believe that you have to use data to design your controllers and update your controllers. So that's also the philosophy that we have in my group, is to develop data-driven controllers. So how do I design our controllers? That's basically given on this slide. Is we have our system, which can be a wind farm. So that's also something I do in this talk today. It can also be a wind turbine. And then we typically build a first principle model, which is basically given over here. But a first principle model doesn't capture all the dynamics of a real wind farm or a real wind turbine. So what we believe is that you always have to augment your model with measurements. And that can be really simple. It can be through Kalman filtering, but it can also be machine learning or whatever. But we believe that you always should merge first principles with data and not full black box modeling. And then we have the model, and then we do controller synthesis. Controller synthesis, a controller is nothing than a computer code, right? So it's just zeros and ones. And what we try to do is always implement. And that's something I'm also going to show for smart wind farms. So this is our philosophy, and that's also data-driven control is also the name of the section I'm heading. So there are some other professors in my section also working on the same cycle, but also on different applications. Although Riccardo Ferrari, here bottom left, in this group of people, is also part of the WaterRide project and also looking at fault detection of wind turbines and wind farms. So working on this cycle, that's something we do in our group, and we do that together with different companies like Siemens Gamesa, Vestas, Eneco, Shell, and also we work closely together, especially in the field of wind farm control with NREL. And we do that with a bunch of PhD students and postdocs, which you can see over here. So the rest of the slides that I'm going to show are also made by some of them. So that's a small disclaimer from my side. So data-driven control, that's how we try to approach it. Now, data-driven control can be done in different ways. You can do this fully adaptive, that your model is updated online, but you can also do it batch-wise. You just build your system, you do modeling with SysID, system identification, then you design a controller, and then you implement, and then you're done. And to illustrate that, and to look at the smart rotor, where we basically started our research in our group, I show you this movie. So in this movie, you see a smart or a blade with a trailing edge flap at the tip. And what we do here is we measure the strains in the root, and we actuate the flap. And what we want to do is build a model from our actuator to our sensor. And in this case, we used system identification techniques. All right, it's going to be interesting. Okay, in this, we use system identification techniques, and then we use traditional loop shaping to design our controller, so PID type of control, and then we close the loop. But what's really nice about this movie is that you see the power of control, that you can really do load reductions with control, with a simple controller. And again, we used here the data-driven control approach. So now let's go back to the wind farm, and let's try to apply data-driven control and also different control technologies on the wind farm problem. So of course, the main objective is to get more energy out of the wind farm, but also taking into account that we don't want to increase the loading too much on the individual turbines. So a recap of what I just stated. So here you see two turbines. You see a turbine with a wake, and there's another turbine standing in the partial wake. A turbine standing in the partial wake will experience a high periodic loading. So you can imagine that the blade passes through the waked flow field and the unwaked flow field. So high periodic loading. And it will also experience a lower mean wind speed, and thus will not generate the same amount of energy as the turbine standing in the free stream. So can we do something about it? Can we not state, hey, let's try to put this turbine somewhere else, right? And of course, you have to do it for different wind directions and wind speeds, and you name it. Is that possible? For existing wind farms, no. But maybe in the future, since you only have to reposition with a diameter or so, maybe that will be possible. Think about the different floating concepts that are out there. Still, this is of course far in the future, but think about the flexibility that you have. If you can do that, the potential is huge because you're fully, you don't have the wake effects anymore. If you can do this in a perfect way. So that's 20% higher energy yield. So that's a prediction. And of course, the loads will be lower because you don't have this strong periodic effect anymore. Of course, this is far in the future. There are also other techniques on how to get more energy out of the wind. And I will talk more about this in the upcoming slides. But what's important here to mention is that it looks so easy, right? I mean, we see the wake in this picture. We have seen the wake on the photograph, but in reality, we don't have that information. We don't have access to the flow information. So the only thing that we have is measurements. So we only have measurements on a turbine level. So what we have to do if we want to do wind farm control, and maybe this repositioning, you have to reconstruct the wind field. Then if you have the wind field, you have to predict what's going on, and then you have to optimize. So that's the big control challenge, I would say. And then you can do repositioning, but you can also use already existing control technologies on a turbine to maximize the energy capture and or to reduce the structural loading in the wind farm. So let's talk about that now. So what are other degrees of freedom that we have? That is, for instance, induction control. So that's given over here. So what is induction control? It's basically derating. So if you derate the first turbine, then it will let energy go. And then you hope that the energy that you let go will be picked up by the turbines in the wake. And then you hope that the sum of the energies will be bigger than the greedy approach that every turbine will try to maximize its own energy. So that's also nicely indicated in this movie. Now, recent results basically show that actual induction control doesn't work. So the energy that you let go is not picked up by all the other turbines. So, and this is shown in field experiments, but also wind tunnel experiments. While if you look at really simple models, the potential is huge for actual induction control. But high fidelity wind tunnel and field testing shows that for induction control, there is a really limited benefit. On the other side, there's another existing control technology, which is called wake steering. And that's something you see over here. And what you do there is you also misalign the first turbine with the main wind direction. And if you misalign the turbine, you can redirect the wake. So what you try to do is that the wake doesn't hit the turbines downstream. And this technology seems to have a lot of potential in wind tunnel experiments, high fidelity simulations, and field experiments. One example is a simulation that you see over here. And this is also something you can see as a state of the art. So you see here two CFD simulations. At the left, you see the baseline. And at the right, you see the optimized setting. So the optimized setting, meaning that we had a first principle model, in this case, the Flores model, developed together with Jan-Willem. And then we optimized the optimal yaw settings. And what you nicely see is that we can do wake steering. Now, in the graph below, you can also see the potential and the amount of energy that you can now extract out of a wind farm. Of course, this is a high fidelity simulation, and still what you see is that the wind conditions are more or less steady, right? It's the same inflow direction, and also the turbulence intensity is more or less the same. So we believe that also if you really want to apply wake steering in a wind farm, you also have to make it more robust with respect to time varying conditions. So what we are doing, and we also did that in European projects and also now some national projects, we look at closed loop wind farm control, also taking the dynamics into account. So what do I mean with closed loop? Closed loop is looking again at the system, and then we also look at time varying conditions. So in this animation, so SOFA simulation, you see that the wind direction is varying. And of course, we know that we have certain control inputs. So this can be induction control, wake steering, or maybe in the future repositioning. Then we have measurements. And please remember that measurements are typically always corrupted by measurement noise. And this can be power measurements, can be load measurements, it can be the wind vane on top of the turbine. And what we believe that we should do is to use this data and combine that with our internal model, which can be the Flores model, but it can be a 2D CFD model or another model, and adapt the model accordingly. So again, I'm coming back to our data-driven approach. This model is then fed to an optimizer, and the optimizer decides over a receding horizon what it will do. So we're basically using the MPC principle. Now, what you see here is basically then again the controller. And the result that you see is one of our latest publications in this field, where we put the Flores model in a closed loop setting, and then we test this for time varying conditions. So that's also the work done with Bart Dukemeyer. So yeah, that's closed loop. So what I believe is essential here is that you look into the dynamics of the wind farm. And I really believe that's the next step. And that's where we can also use control theory. Still, I'm talking here about using steady state control inputs like yaw misalignment or induction control or repositioning, which is all extremely slow. Our recent hobby in our group is also to look at dynamic actuation. And that's basically the next topic I would like to address. And that's wake mixing. And I will also try to make the link again with floating wind. So wake mixing, and then I would like to look into dynamic actuation. So what do I mean with dynamic actuation? If you do induction control, you basically derate your turbine. So you have an offset, for instance, in your pitch, or you change your generator torque. Now let's use pitch. So you basically pitch out the blades a little bit, and then you'll lose some energy, and you hope that the downstream turbines will pick up that energy. As stated before, in steady state, that doesn't work. But what will happen if we do this in a dynamic fashion? So what will happen if we do dynamic pitch, for instance, sinusoid on the pitch? And think about really low frequencies, a frequency around 0.2 Struhal for a 10 megawatt turbine. That's a frequency of 0.01 hertz, order of magnitude. So we call that the pulse. So I will give an animation later on about the effect. And that's the innovation also from our group, is to do this in a different way, is to use individual pitch control. So I didn't explain individual pitch control, but individual pitch control is typically used for load mitigation. But if you apply it in a certain way, then basically you can also try to steer the wake. And then the wake will get some kind of helix shape if you do the pitching in a certain way. So that's again explained here. So the pulse, we just put a low frequency sinusoid on the individual pitch angles. And the helix, then there are a little bit of details about individual pitch control. You basically put a low frequency sinusoid on the tilt and yaw degree of freedom of a turbine. If you do that with the MPC transformation, you get the 1P pitching plus or minus a certain frequency. I'm not going to talk here about the details. There are some nice papers written about this. So the point here is, can we do something with dynamic actuation? And then of course it's yes, because otherwise I wouldn't show you the results. So here again, a SOFA simulation with uniform inflow, with a single turbine, 10 megawatt turbine. And then here, the second one, you see the pulsing. So if you do pulsing, you see that you get wake mixing, and you also see that the power on the first turbine fluctuates a lot. And that makes sense because we're doing this collective pitch. And then we also have the helix. And with the helix, we do individual pitch control. And in principle, we don't touch the collective pitch part. So that also means that the power will stay the same on this turbine. And what you nicely can see is that also the wake gets a helix shape. So that's fantastic because we also have more or less the same amount of wake mixing. And here you see the full potential if we put a turbine in the wake. If we now have a turbine in the wake, you see that we go from 6.1, 7.2, 8.2 megawatt if we have full wake interaction. Of course, this is the perfect scenario, uniform inflow, but we have shown that also with turbulent inflow, there is a gain for this technology. And we're now also exploring this further in national projects, and we're also going to do some field testing of the different technologies presented over here. So that's wake mixing. I know that Daniel is also going to talk in this session, but I'm going to do a spoiler alert a little bit. What will happen? Oh, that's later on. So part of this technology, so this wake mixing, the pulse, we already tested in our own wind tunnel because we always believe it's important to also test our algorithms, either in real life or in a wind tunnel. So we use the Open Jet facility here in Delft. So here you see a person standing in the wind tunnel, so you get an idea of the size. We did some PIV measurements. So we have this bubble seeder. We have a small turbine. We have a couple of these small turbines to do wind farm studies. So we have 4 of these small turbines, diameter 60 centimeters. And what we did is we changed the pitch. In this case, only collective pitch. Now, if we do that, and then you get these kind of images if you just put a video recorder in your wind tunnel. And here you nicely see the pulsing. So you nicely also see the pulsing in the wake. And if you then do the PIV analysis, and this is the work of Daan van the Broek. No, Daan, I forgot his last name. Okay. If you do that, then you get these kind of images. So what you see here is again measured the pulsing, and what you nicely see is that you get the wake mixing. So the wake mixing, what we have seen in high fidelity simulations and the concept, it's real. I mean, it's also going on in wind tunnels, and we have done something similar in the wind tunnel in Milan, part of the European CO Windcom project. And then we also put a second turbine in the wake. And again, we showed some benefits of this wake mixing. So here's a spoiler alert. So I'm going to be quick here because I think I have an hour in total. can we not combine it somehow with floating? So this is a picture I've taken in the Dutch or the Rotterdam harbor. At the right, you see a GE turbine, one of the biggest in the world. And here you see a floating turbine, which they're constructing in this harbor and then bring it, I think, to Scotland. So can we also not use floating turbines to enhance wake mixing if you also do something with pitch? So Daniel will give you the details, but if we, for instance, do it with the helix, then you can imagine if you apply the helix and you apply also yaw and tilt moments on your rotor, you also get a natural movement of your turbine. Now you can do this for the helix, but Daniel is also going to talk about the pulse. You get something similar. And then the main advantage would be is that the amount of amplitude that you need for your pitch can probably be reduced. And that's what we see over here. So similar animation as before. So baseline with 2 turbines, helix 1P with 4 degrees amplitude of the pitch. And then here we see the floating implementation. And there we only have 2 degrees of the pitch. And more or less the total energy gain is the same. So what I'm saying here is that we can exploit the dynamics of a floating structure also to get a little bit of wake mixing for free. And that's something we're also now exploring. And that's part of a European project called FlowTech, which started earlier this year, where we look at wave mixing techniques for floating structures and also looking into wave feed forward. So yes, so the take home messages, and then we have time for questions, is data-driven control. So that's the philosophy that we have. So that's the synergy of combining data with models. So not fully black box and also not fully relying on models. And I believe it's really the way forward to do control of complex systems. And especially if you look at wind farms. And I also would like to say that this is more than just applying machine learning, because it's really also taking the physics into account. And then if you look at smart wind farms, I'm only talked about some of the technologies we're working on. There are so many new technologies that lie ahead of us. So especially this wake mixing, which is one of our favorite hobbies at the moment. And I dare to say that wind turbine control and wind farm control is now really becoming control of high-tech systems. Now, having said that, this is basically the summary of the work that we are doing in Delft within my group. We're working on floating wind farms, where you might have these smart actuators even on the blades to do something about load mitigation. You can have LiDAR. We're also looking into floating installation, and we're always interested in novel concepts. So that's why you also see that at the top left. But the most important thing that we do is we build the algorithms around it, because having an actuator, having a sensor, that is not sufficient. You have to add the knowledge, the intelligence behind the system. And then again, we talk about the zeros and the ones and the algorithm development. And that's basically the field of systems and control. And that's what we are doing. And I think we will see more talks in this session related to this topic. And I believe I'm exactly within time. So thank you very much for your attention.
Great, Jan-Willem. Thanks a lot for the really interesting presentation. And we do have a number of questions, which also shows, I think, the interest and the clarity of your presentation. So Francisco is asking, what would be some of the challenges of implementing those active control systems on full scale, so 10, 12 megawatt offshore wind turbines?
So there are many. If you look at let's start simple, just wake steering, floors and misalignment, There's now a commercial product, Wake Adapt. Siemens Gamesa has that product. And then you have to do all the safety checks. Because if you change something in the control logic, then all the safety checks have to be done for loads, power production, and you name it. So if you want to go to advanced control and to do the implementation, a lot of checks have to be done. What we are going to do is we're going to do wake mixing, and that's relatively simple for now because that's an open loop signal, and then you can just put it on top of your existing control system. However, then still you have to do all the safety checks and look at all the loads. So implementation wise, on paper it seems easy, but for industry it's quite a big step. I'm not sure if that answers the question, but it's far from straightforward.
Yeah, thanks. Another question about your comparison of the pulse and the helix. So Andre is saying the pulse demo shows the upwind turbine generating more power than the baseline upwind turbine. Is this a fair comparison? You could also pitch the baseline upwind turbine to generate more power in a steady way.
So on average, it's not more, so it will drop a little bit. But you can imagine that if you do the pitching, then you also have the inertia and stuff like that. So at some point you have more energy, but on average it will be lower. Then the question is, can you also then do the induction control in a steady state way? And of course we have done that for this simulation. And there is a small benefit. Then we talk about 1% or something like that. But if you add turbulence, then that gain is gone. So that's also my statement regarding actual induction control, that there is not a big gain. And that's also something we see in high fidelity simulations. So hopefully that answers the question.
Yeah, and I think he had another comment, so I'll jump there. He said this might apply to the helix case, but if a single blade is much more loaded than the baseline blades, would increasing the loading of all three blades of the baseline be better?
I think all the blades will experience a much higher loading because we pitch the blades every rotation, all the three blades. So the loads will definitely go up. So that's the big disadvantage of the helix approach. Mm-hmm. So the concept is also that you don't full-time run the helix, only in situations where you have full wake interaction. And now we're also exploring different input signals to really minimize the loading. And then I'm talking about the loading mainly on the pitch bearing, because that's the important one. The blade loads will slightly go up, but the most important one is the one on the pitch bearing.
Yes, because I was also wondering, so you show on the power, but indeed in terms of loads, yeah, you need to be careful with this, I guess, helix. Yeah.
Absolutely. But that's also the nice thing about being in academia. We can come up with these crazy ideas, and some of the ideas will find their way into industry. But of course, loads is a big disadvantage of the helix approach. And we're still looking at the details of that. So we just submitted the paper looking into the loads of the helix. So hopefully that will appear soon.
Okay, great. Then another question. So Carlos Navarro is thanking you also for the presentation. In the cases you described where a misalignment, either pitch or yaw, was induced on the wind turbines in the farm, is it possible that these movements are done by all the wind turbines affected at the same time, or on the contrary, is it necessary to stop part of the wind farm to perform the corrections?
Yes, so the biggest gain, you will get that if you only do it on the first row. But there's also a lot of research now going on. What will happen if you do also misalignments in the downstream rows? And at some point it will stop, right? I mean, if you're really far in the wind farm, a little bit of misalignment doesn't help anymore. So at the end, it's a big optimization problem. And I think it's a time varying optimization problem. And it really depends on the wind conditions. So in principle, all the turbines should have the freedom to have this misalignment. but the amount of misalignment will vary. But for sure, you should do it for the whole wind farm.
Thank you. Then I think the two remaining questions are actually related to the fatigue that we just, so I'll read them, but maybe we already kind of answered them. So the actuation that transforms the wake to an helix form seems really promising. However, what can be said for extra loading and imbalances due to this continuous pitching that is also different per blade? Doesn't it increase fatigue? So I think you answered that probably already. Don't know if you want to add anything.
Yeah, so what I would like to say for the pulse, that's really low frequent. So then the effects are not that high. But for the helix, of course, we are doing individual pitch control. So the loads will go up. And we have now some numbers, and we now submitted that to a journal. But the main concern is the pitch bearing, and the rest is relatively okay. And of course, it's a trade-off between creating more energy or having higher loads. And you can imagine that this trade-off will vary depending on the situation the farm is in.
Right, and on this topic as well, Francisco is asking if there are any studies on the potential fatigue load cycles or reliability impacts imposed by these wake mixing strategies. So apart from the paper you mentioned, do you know any other studies?
For collective, yes. So for the pulse, yes. So we also have done that. There is a paper in Wind Energy Science where we study the loads. But for the helix, I think we have now the first publication out regarding the loads.
Good, and we have for now a last question, a little bit off topic from your last slide, which we can still see. It shows a floating installation vessel installing a floating turbine. Is there a story behind this representation? And have you considered similar control strategies applied to installation for improved workability? Yeah,
so thank you for the question. So in fact, we will be present during a floating installation. So it's not a floating turbine. It's a normal bottom fixed turbine, but from a floating platform. And these experiments will take place in September. So then we are going to measure. So we're only going to do the data-driven modeling, but then later in that same project, we are going to do data-driven control also for installation. So for now, we are going to equip such a device with many sensors to do data-driven modeling. And then later on, we would like to apply this data-driven control for floating installation. So that's the inspiration of that, the movie. And that's the work done together also with Herema.
Okay, great. We have one question which just came in. Have you ever checked what would happen if you mix one line of large turbines and the following line with smaller turbines? The density of the turbines within the farm would increase. How do turbines at different hub heights affect each other?
No, so I've never studied that myself, but that's something that people really look into, to also look into the optimization. And then I think you are also approaching a cost issue. So I don't know the details, but I'm sure that people are looking into wind farm optimization and also different turbines, placing them in a farm. But personally, I never looked into that.
Yeah, I'm aware there are a few people looking at mixing so that maybe you harness some of the leftovers, or but I think in terms of standardization, maybe and develop this on a large scale, there are other, I guess, constraints in effect. Thank you very much, Jan-Willem. I don't see any more questions for you, but I think it was really, really interesting. And I think people know also how to find you, how to contact you if they have any more questions or discussion topics for you. So again, thank you very much for joining us, and we look forward to hearing more also about your spoiler with Danielle. So
very good. Thank you very much. Have a great day.
Yeah, you too.
Bye.
Bye. So now we'll move on to our short presentations, and the first one that we have is from Javier Lopez from Tecnalia, and he will talk about floating offshore wind turbine vibration control. Javier, I think you can share your screen. Yeah. Yeah, we see the full screen.
Can you hear me now?
And
yeah, I think
hear
so.
you. Yeah,
okay,
great.
thanks. Good morning, everyone. My name is Javier Lopez. I'm a second-year PhD student at Tecnalia, and I'm working in floating wind turbine control. I would like to briefly introduce you to this research field. The slides are divided as follows. First, an introduction to then move to the main topic of the presentation, where I will tell you the influence of the controller in floating wind turbines. Next, I will talk about which are the alternatives for vibration control. In a last slide, I will briefly present the control co-design methodology. And finally, some conclusions and references will be presented. So let's start. What is TWIND? TWIND is a project where a consortium of 4 different entities create a network of cooperation to impulse offshore wind energy research and industry in Portugal. So thanks for the opportunity to be here presenting this topic. Moving to a presentation core, let me explain how a wind turbine works. The control strategy describes how the turbine is programmed to approach in a steady state the ideal power curve. Commonly, commercial wind turbines allow a variable speed and variable pitch operation. The control schemes and objectives are different for each region. In region 1, the wind speed is too low to produce electrical energy and the turbine is kept in standby. Region 2, below rated wind speeds, the turbine starts producing, so the control objective is to maximize the output power. In this region, the blade pitch angle is usually kept constant to a value and the generator torque is controlled. If the turbine operates in region 3 above rated wind speeds, the control objective is to maintain the power production to the nominal value. This is done by a proportional integral controller, which uses the generator speed error as a measure to set the blade pitch angle, as can be seen in the formulas. In this region, the generator torque is commonly set as an inversely proportional value to the generator speed. In the region 4, the wind speed is too high to produce energy safely, so the wind turbine is shut down. For floating, the challenge appears for wind speeds above rated value, precisely in region 3. The previously presented strategy generates an instability when it is applied to a floating system when we are operating in region 3. So there's a problem with the wind turbine controller. A typical wind turbine employs a pitch to feeder strategy to control the power up. When the wind speed increases, the blade pitch angle also increases to reduce the thrust force. This can be seen in the figure. In a floating system, the thrust force is a damping force for the system motion. When a change in wind speed is a positive change of the thrust force, the damping is positive. But when it is negative, a negative damping is introduced to our system, increasing the motions. This negative change can be seen in the thrust force when we are operating in region 3. So why is this a problem for the controller? Assume an increase in wind speed. The platform pitches with the wind and the aerodynamic torque increases, so the pitch angle needs to be increased to maintain the power to the nominal. In this case, the thrust force is reduced. So we are in a negative damping situation. Now assume that the platform pitches to the incoming wind. The only way to stabilize the platform is to create a restoring moment using the thrust force. So we need to increase the thrust force by reducing the pitch angle. Both control objectives are competing to control the pitch action in region 3. This is an undesirable phenomenon that increases the loads and reduces the power performance in floating wind turbines. So how can we control this and reduce loads? First, using the wind turbine control. Different complexity level controllers can be designed to solve this. In a first level, we can use the same CISO control that keeps the basic control structure. The difference between this and the previous explained control is at the tuning of the control gains. This reduces the controller bandwidth below the platform pitch natural frequency. A gain scheduling method are proposed because the influence of the instability is critical only in certain operating points. However, reducing the control gains leads to higher variation on the controlled variable. For example, higher variation in generator speed will increase fatigue loads on the drivetrain. If we add additional sensor, a better control performance can be obtained. For example, we can add the tower top acceleration to the controller to reduce the influence of the pitch motion. If we add extra actuators, a decoupling of the generator speed control can be done. The main advantage of this is that the aerodynamic thrust is not directly affected by the controller. And then finally, advanced control methods based on models such as LQ, approach, H-infinity, or model predictive control has demonstrated several advantages. This kind of controllers has been used to avoid or at least reduce the instability and to reduce loads. Other controllers that we can use are the individual pitch control that allow us to control each of the plates independently. This has demonstrated that solves the stability problem and reduce loads. Another option is to use pitch to stall strategy instead of pitch to feeder that inherently eliminates the negative damping due to the blade geometry configuration that increases the thrust force for each wind speed as can be seen in the figures. Finally, artificial intelligence methods are being developed for floating offshore wind turbine control. Apart from stabilizing the platform, these strategies allow us to reduce wind turbine structural loads. The previously presented control strategies are capable of reducing the wind loads and controlling wind turbine response. However, they present some drawbacks. First, the loads reduction is limited. Second, they have a higher usage of the actuators. And third, they would lead to power fluctuation. So this means that a compromise between load reduction and power performance is needed. If we change the approach and we use structural devices, will allow us to reduce the wind turbine vibration. These methods are divided into 4 categories: passive, active, hybrid, and semi-active methods. Passive control devices does not input any energy into the system from the controller, and the control forces are generated using the structural motion of the system. Different energy dissipation devices are proposed in the literature and installed in wind turbines. For example, tune mass dampers located in the wind turbine nacelle. The key to design one of these, like the 1% in the figure, is to tune each frequency to the frequency of the motion of the main structure we want to reduce. So the device will resonate out of phase with the main structure, dissipating energy. Active control devices can effectively reduce the structural vibration. However, they use the same concept, but require external power to input energy, which make them not applicable when there is a power failure. Hybrid devices combine the passive and active systems. The passive control achieves part of the control goal, so less energy is transferred to the active system and less external power is needed. Semi-active devices are similar to the passive devices, but we can change some of the system characteristics, such as the stiffness or the damping ratio, to achieve a higher energy dissipation than a simple passive device. With the previous slides, we have finished the different controllers for wind turbine vibration reduction. All of them follow a sequential design process, where first the wind turbine is adapted from an onshore wind turbine model. Then the substructure is designed based on wind turbine and tower characteristics. Next, the moorings are designed, and finally the system control is designed and tuned to fit the system dynamics. So what if we optimize all together? This is what the control co-design methodology do. If this methodology is applied for the early design steps, an optimized design would be achieved for any subsystem we decide. With this, a reduction of cost is expected. Each of the previously mentioned control strategies or approaches will lead to different optimal designs, and different projects are now being done using this kind of methodology. For example, those funded by the US Energy Department to ARPA agency in the Atlantis program. So this is a really interesting field to work on with many possibilities. Some conclusions that can be highlighted are two different approaches can be followed to reduce vibration in floating offshore wind turbines: the wind turbine control or adding a structural device. Different control strategies based on model are promising for floating offshore wind turbine vibration control. New sensors allow the use of onshore controllers for floating offshore wind turbines, increasing the power performance. Structural devices reduce in a large amount the vibrations. However, they add costs due to a new subsystem and increases overall complexity. Co-design methodology would achieve a reduction of the leveraged cost of energy if it is planned from early design stage to the commercial stage. If a structural method is thought to be used in a co-design methodology, the obtained results should be competitive in cost compared with a typical controller. And here are some of the references I used for the presentation. More reference, and that's all. Thank you for your attention. I hope you liked the presentation. If you have any question, I would be glad to answer them in the Q&A session. Thank you very much.
Thanks a lot, Javier, for the nice presentation. So I just said we will treat all the questions at the end of the short presentations. So please do post your questions in the Q&A tab, and we'll come back to them after the two next short presentations. So our next speakers, there are two names. So I guess you will share the presentation. These are Michael Smailes and Ampea Karikari-Boateng from Catapult, and they will talk about wind turbine and wind farm control. Please go ahead.
Thank you very much. Yes, so my name is Michael Smailes, and my co-presenter is Ampea Boateng. We're here to give you a presentation on wind turbine and wind farm control. Maybe a little contrary to other presentations that you hear today, this will be a very high-level overview of the different control levels within a modern offshore wind power plant, from the wind farm controller all the way down to typical large-scale offshore wind turbine converter control, and the various interactions and responsibilities. To this end, I will first give an introduction to some common wind farm control terminologies, as the term can mean slightly different things to different people, especially across different disciplines. I'll then take you through wind power plant control before handing you over to my colleague Ampea to go through wind farm control as well as wind turbine control. Finally, I'll give you an overview of wind turbine converter control. So, recent advancements in wind farm control have started to bring together multiple different engineering disciplines with sometimes contradictory definitions for the same technical terms. To ensure that researchers from different disciplines can talk to each other, it is important to define a common set of terminologies. To this end, research institutions from across Europe have released a number of conference and journal papers to define such terms through the project Farm Corners. To this end, the following terms are defined as follows. Here, wind power plants encompass the turbines and balance of plant equipment and are there to serve grid code. This is slightly different to what you define as a wind farm, which normally just includes the wind turbines themselves, not necessarily the cables or any of the other balance of plant equipment. Wind power plant control is at the moment very well established and has been around for multiple years, and it's designed to comply with the local grid codes and grid integration. So it's more on the electrical side of things. While wind farm flow control is a more recent development and is only in a few instances being instigated in commercial wind farm projects. And it's aimed at maximizing power extraction and or load alleviation on offshore wind turbines. Wind farm control, which is sometimes used as a synonym for wind farm flow control, is here defined as an umbrella term for wind farm flow control and wind power plant control to coordinate operation of wind turbines within a wind power plant to serve a common goal. Wind turbine control is the central controller on each turbine and controls the turbine's energy production, load reduction, and general safety aspects, while a converter control is responsible for enacting electrical set points given to it by the wind turbine control. As you can see on the right, each of these control levels have different response times, ranging from a few microseconds up to potentially several hours to days. The rest of the presentation will discuss each of these control levels in a little more detail. So starting with wind power plant control, as I mentioned before, this is mostly aimed at grid code requirements. So grid code details all the technical requirements that must be complied with in order to connect to or use the grid. This includes mandatory ancillary services such as limited frequency and reactive power support, but also grid ride-through capabilities. It also manages the electricity market commitments. So energy generators have to bid into different energy markets to sell their electricity. These range from very long term, which generally isn't used for offshore wind, to relatively short term. And any bid that generators make into these markets, they need to comply to. So this is more to do with the power management. So the wind power plant control has to coordinate how much power is given, how much power is produced by each of the turbines within the farm. And then finally, there's also an ancillary service market. So this is in addition to the power market, generators can bid into a market to provide additional services to the grid in order to stabilize the grid and allow customers to receive a stable and secure supply. So moving more into what the future for wind power plant control will look like. As we move towards the latter part of this decade and certainly towards 2050, variable renewable energy sources will make up a significant portion of our offshore grid, which will not only create slightly more potentially unstable grid conditions, but also potentially lower average prices. At the same time, subsidies for offshore wind will come to an end, or at least diminish over the coming years. So this will push wind farm owners to look for additional revenue streams, for example, through ancillary service provision. And that will drive wind farm owners to move from maximum power generation to maximum revenue generation, as these two terms will become distinct. And balance the grid in the future with all of this new variable renewable energy devices. New ancillary service products will be created and will be available for wind power plants. These include black start, inertia support, fast frequency response, and harmonic suppression. With all of this, wind power plant control will have an increasingly complex interactions with the wind farm and different levels of the control. So it'll become more important to have comprehensive testing to ensure that this, along with the other generators within its local vicinity as expected. So I'll now pass you on to Ampea to give a high-level overview of wind farm flow control.
Okay, thank you, Michael. So basically, for most of the things I'm going to discuss, I think Jan-Willem and Javier have touched on some of these aspects, so I will go through some of them slightly a little quicker, so that it's not too repetitive. But wind farm flow control is one of the control techniques, or rather a group of control techniques which aim to optimize the power from a wind farm perspective, and also reduce load from a wind farm perspective rather than individual turbines perspectives. So the wind farm flow control basically coordinates between different wind turbines to achieve this control goal. So there are quite a range of different techniques which are can be applied to do this. So there's the axial induction control, there's wake steering, wake mixing, and also for things like floating offshore, potentially we can reposition turbines. So the whole point of wind farm flow control is that when the wind goes through a wind turbine, there are some downstream effects, and essentially these reduce the power or energy available to some of the turbines downstream. Also, the increased turbulence can increase loads on some of the turbine components. So if you see from the figure on the right of wake steering, we've got A, B, C in the figure. Basically, if you look at the A section, that shows you how wake steering is achieved by controlling the yaw of the wind turbines. And you can see in the color from B, which shows how much energy is in the wind, and the blue section shows the velocity deficit, so how much velocity is lost by the wake. C shows the potential effect of wake steering on general turbine, the general energy available to wind turbines within the wind farm. And you can see that with the wake steering case, the darker blue areas are not as dark, so there is more energy available to those wind turbines. So that is one of the key aspects of, or one of the most popular and most advanced form of wind farm flow control. So this is achieved through the wind turbine control, which we'll discuss a bit more. Yeah. So we've discussed about the wind farm controller. Michael introduced the wind farm controller, and the wind turbine controller is specific to individual turbines, rather than looking at the turbine from the rather than looking at the farm level. So if you see the figure on the top right, you can see in the black box is indicative of the task or the functional breakdown of some of the things that the wind turbine controller does, and that interacts with the wind farm controller. So the wind turbine controller in itself doesn't actually do all the control by themselves. They interact with dynamic component controllers. So within that, the wind turbine, there will be subsystem controllers for the pitch control, for the yaw control, and also for converter control. So the point of the wind turbine controller is to look from a high level, control the power production, control starts, stops, events, and also make sure that during the power production stage there is optimization in terms of optimized power capture through both speed and torque control. So one of the other things that the wind farm, wind turbine controller tries to do is to reduce loads. So overall, the turbine controller is often designed based on a dynamic model of the turbine. So at the top, it shows like a dynamic representation. At the top, you've got a dynamic representation of a system. So essentially, you can represent the turbine components using things like spring mass damper systems. And through there, you get your time domain response and frequency domain response. And you can design a controller within a control loop, which controls this. So which controls the dynamic system. In addition to doing that, to achieve your control goals, we also build in some additional load reduction strategies. So we want to avoid things like resonance. So at the bottom, you see a Campbell diagram of a wind turbine, and basically from this Campbell diagram, we can identify resonance points within the potential resonance points within the turbine. And in the controller, we can design filters. So for example, we can design NOT filters or bandpass filters or high pass filters to eliminate certain operational regions so that we avoid resonance. In addition, one of the popular strategies which are used to reduce loads on the turbine structure is also the implementation of individual pitch control. So this is more or less becoming more and more mainstream. And you can see from the figure on the right that compared to using collective pitch control, you can have quite a lot of load reduction when individual pitch control is used. But one of the key aspect of wind turbine is to extract energy. So the next slide. Is talking about the power production control strategy. So more or less, the wind turbine controller tries to follow a specific power curve. And within the power curve shown at the top, there are different control goals within these different regions. In the region 1, basically, whilst the turbine is, the turbine hasn't reached rated speed, we want to extract as much power as possible. Whereas in region 3, we cap how much power we want to extract to the rated speed. So this is done using a range of different controller algorithms. Because of time, I'm going to skip, not go into detail, but Javier mentioned a bit about the PID controller, which is the most popular controller technique that is employed. But there are other advanced controllers available, which are also being researched. So the key things that the turbine tries to control is it tries to control the torque, and it also tries to control the pitch angle, and that in turn also controls the speed. So in addition to controlling these speed control and torque control can also be achieved with the converter control. So Michael will talk a little bit more about converter control.
Thanks, Ampea. So very, very quickly, just to wrap up, the last stage within the converter, within the wind farm control segments is the converter control. So this is much faster acting. It's generally within microseconds to milliseconds. And within modern wind turbines, there are two converters. So one is the drive side, so controls the turbine generator, and the other is the grid side, so interacts with the power grid. The main purpose of the converter is to enact what the wind turbine control is told it to do, or what it desires to do. So in the drive side, that is in terms of controlling the torque or speed of the generator to ensure that it's tracking the maximum power point tracking, or to achieve load reductions by fluctuating the amount of power that is extracted from the turbine. On the grid side, it's mostly about ensuring that the correct amount, that the right amount of reactive power is produced to support grid voltage, or to increase or decrease temporarily the power output. On the grid side, this is done through first measuring the current voltage at the measurement point, transferring this normally to DQ, so parts transform, and then do a inverter control. This is generally two-level. One is a slow, comparatively slow power control, and then much faster current control to output the correct voltage and power at the output. Here's an example of the power control and current control for a simple turbine. More modern, or research is currently going in to look at replacing this kind of control with a virtual synchronous machine to improve the inertia within the grid and help maintain a more stable frequency to allow more variable renewable energy sources to connect. So very quickly in conclusion, wind farm control is an umbrella term for wind power plant control and wind farm flow control. While power plant control has been around for some time, farm flow control is slightly newer and is about maximizing power output or load alleviation. Both wind farm flow control and power plant control feed signals to the individual turbine controller, which actually enacts the desired set points. The wind turbine control is responsible for energy production, load reduction, and safety of the individual turbines. Wind turbine control is a supervisory control which interacts with the subsystem controllers such as pitch, yaw, or the converter. While the converter is responsible for realizing the voltage and current, real and reactive power set points determined by the wind turbine controller. Okay, so thank you very much for your attention, and apologies for running slightly over.
No problem at all. Thanks a lot, Michael and Ampea, for I think the presentation, which was nicely complementary to the previous talk. So I think that fits nicely in. Thanks for that. Again, put your questions in the Q&A and we'll address them shortly after the session. So the last short presentation of this morning is from Daniel van den Berg from TU Delft, and he will talk about enhanced wake mixing with floating offshore wind turbines.
Yes, you can all hear me?
Yes, we can, and we see
Good.
the slides.
All right, nice. So yeah, thank you for letting me rounding up this session. So in the next 15 minutes or so, I'm going to be talking about enhanced wake mixing, something we've already heard about from Jan-Willem. But now we're looking at floating offshore wind turbines, and then also with the idea of what we also already heard of controls co-design in combination with this offshore floating wind turbine, how we can use this for optimization for wake mixing. So for this presentation, I'll first quickly reintroduce the wake mixing strategies. We've already seen a lot of it again during Jan-Willem's talk, so that makes my presentation a little bit shorter. Then we'll go into a little bit more detail. So what happens when we apply these methods on a floating offshore wind turbine? What kind of motions do we get? Is this what can we expect from our system? Then we'll showcase some preliminary results based on some case studies we did for different wake mixing strategies. And then finally, rounding up the presentation, I will talk about future work and the scientific prospects based on the results we saw in the case study. And then we will specifically aim again at this, what I call the co-design triangle. That will become clear at the end of the presentation. But first, for those who might have just tuned in or maybe missed it from Jan-Willem's presentation, typically speaking, we have what we call wake mixing strategies, which are strategies by which we actuate the blades of the turbine to cause wake mixing. With wake mixing, we can increase power generation of turbines downstream by having the wake re-energized at an earlier stage. And typically we discern between two different methods, the pulse and the helix. With the pulse, we pitch the blades simultaneously in a sinusoidal manner. And with the helix, we also are pitching the blades, but then individually with a certain phase offset. And then the results on the wake are shown in this movie, which is probably, again, not really new for most of us, and we've seen it just now, but I'll quickly go over it. So here on the left, we have a turbine running baseline, so that's just greedy power settings. Then again, we have a turbine running the pulse, and there you can clearly already see this pulsing effect in the wake. Then at a certain point, we will add a turbine doing the helix. Let me skip a little bit ahead. So here we have the helix, and again, we see, again, why we call this method the helix. We see this a typical helical shape in our wake appearing. And then finally, when we add, skip ahead again. So when we add a second turbine downwind, so we make the smallest possible wind farm that we can have, 2 turbines, then we can see that our second downwind turbine is producing significantly more energy with the wake mixing strategies compared to a baseline. So these techniques and results already exist. They have been simulated in many different programs, and there is merit to it. But the real question we're looking at is, okay, when we are applying these wake mixing strategies, we're also varying the thrust of the turbines. We also saw a short movie in Jan-Willem's presentation of this. So for example, with the helix, our thrust force will get a lateral movement. And then, of course, the interesting question is, because our turbine is now floating, because this platform is free to move, we can also expect some kind of pitching or rolling motion from our platform, maybe even translation motion. And then, is there a way we can actually use this kind of movement from our platform to maybe enhance our wake mixing further? To get an idea of what our platform would do when we apply the pulse or when we apply the helix, we took the DTU 10 megawatt on the triple spar platform. This is a model which has been well researched, and there exists a model of it in fast. And for a whole range of Struhal numbers, so that's different frequencies of pulse and the helix, we logged all the motions of our platform in steady state. And from that, we extracted so-called Bode plots. So what these Bode plots show, and I'm only showing now the rotational motions of the platform, because the translational motion in the end turned out to be negligible in comparison to the size of the turbine, but the rotational motion turned out to be quite significant. So what we're looking at, if we take, for example, the top left graph, so if we apply the pulse with, for example, 1 degree of blade pitch, then at the ideal Struhal number of 0.25, we can expect roughly 0.25 of platform pitching. So that's backwards and forwards pitching of our platform. At the same time, we can also see that at this frequency, we have some coupling to the yaw motion. So the yaw motion is also amplified at this frequency. And we can also see that we have roll motion, but this is of 2 orders of magnitude less. So our platform, when we apply the pitch or apply the pulse, as you would imagine, because of this varying thrust, which we also saw in Javier's presentation, our platform will start pitching backwards and forwards. And if we do this in a cyclic manner, then also our platform will be pitching in a cyclic manner. And it's typically the pulse is applied with 2 to 4 degrees. So let's say we take the pulse at 4 degrees, our platform will be pitching with plus to minus 1 degree. So it is a motion that we can actually see on our platform. Now, if we look at this at the helix, we also see something interesting happening. So first of all, for the helix, as we also saw in Jan-Willem's presentation again, is that the helix amplifies the yaw motion quite heavily. The reason also the yaw motion is amplified this heavily is because it's not naturally damped by the water. So pitch and roll motion are naturally damped by the hydrodynamic forces. This is not or less the case for the yaw motion. And we can also see that around the ideal Strual number, so the ideal excitation frequency, we have a significant amount of platform amplification. So this is interesting because let us assume that this yaw motion we get from the helix is actually very beneficial for the wake mixing that we want to achieve, or maybe even wake steering. Then it will mean that with very little helix input, we could already achieve a significant amount of wake mixing or wake steering. So this is also interesting from the perspective of controls co-design. Maybe we can use the fact that our platform is amplifying this motion so heavily. It must also be noted that we say ideal mixing frequency, but for the helix, we do not yet know what this ideal frequency is. So what we know now is that, okay, if we apply these methods, as expected, our platform will be moving. And it's also quite a significant movement. So it's not like 0.1 degree, but it's degrees. And especially with the helix, again, we have significant yawing motion from our platform. So to see what kind of results we could expect in terms of wake mixing, we devised some case studies to make a comparison. So these scenarios are all based on the DTU10 megawatt on the triple spark platform. Again, this is also the platform on which we have based our body plots, and also it's a well-researched, well-documented platform combination. It's only a platform combination or turbine platform combination that I think exists in literature. Nevertheless, we took so for the pulse, we took 4 scenarios. I see that I'm missing one. So for the pulse, we took 2 degrees of blade pitch without platform movement, and we also took 2 degrees of platform movement with half a degree of, or 2 degrees of blade pitch with half a degree of platform movement. Then we double the blade pitch. Oh, I see. This is complete. I made a few typos here. So we have 4 scenarios: 2 with 2 degrees of blade pitch, 1 without, and 1 with platform movement, and also then again 4 degrees of blade pitch, and 1 without platform movement and 1 with platform movement. And the goal is to see what's the incremental increase in wake mixing, if there is any, between the various scenarios. Then for the helix, we also did something similar. So we have the 4 degrees of blade pitch without platform movement, and then we halve the blade pitch angle, and we allow the platform to freely move. And as of now, we have prescribed, and this is important, we've prescribed the motion of the floater. So we apply the pulse, we apply the helix, and then we tell the system, okay, yaw or pitch our turbine in this way. So there's no coupling between our floater model and the aerodynamic forces as of yet. It is something we are working towards as of now. So if we first start with looking at results for the pulse. For the pulse, we're now looking at a movie of a front view of the wake at a 5D distance downstream. And we chose 5D. This is a typical distance where you would want to place a second turbine. And then we're looking at the average wind velocity over the rotor disk of any potential second turbine that we can place there. And it's also plotted in real time in the graph down below. And then we're looking at average wind speed because in Q-Blade, we're not capable of placing a second turbine downwind. So we have to get a measure of the amount of energy that we can extract. We are looking at the average wind velocity. The results are also summarized in the table below. So here you can see that no matter what we do, if we start pulsing, then we have an increase in average wind speed across our rotor disk. This is also what we expect from literature. This is a known result. However, which is something which is far more interesting, is that if we allow our platform to pitch, we get a significant improvement in the average wind velocity that a second downwind turbine would potentially feel. So this is an increase in wake mixing in our system coming purely from allowing the platform to move. And we can also see that that even for the 2 degree case, with this particular data set, allowing the platform to move is equivalent of doubling the amplitude of the pitch of the blade pitch without allowing without any platform movement. So there's a significant increase in wake mixing by just allowing the platform to move. We see something similar for the helix. So again, on the left, we have the baseline simulation. Again, this was done in SOFA, so we have a different movie now. Then we have the helix with 4 degrees without any platform movement, and then the helix with half the blade pitch amplitude, so only 2 degrees, but now it's allowed to yaw from side to side. And we actually see that our total mean power production is slightly higher for the second case than with the helix without any platform movement. This is also extremely interesting from the perspective of what Jan-Willem also talked about, what UBC's question was, loading. Because it means that we can actually reduce the pitch amplitude, so increase the loading, while still achieving similar or even better results for wake mixing. So to wrap up this presentation, for now we've seen that for both the pulse and helix we have very promising results. Allowing the platform to move, again, it's a simplified scenario. It does increase wake mixing. It's also interesting that the amplification of motion, of the platform motion, is primarily dependent on platform parameters. So the turbine itself does not play a significant role. It does play a role, but not significant. This is also interesting from the perspective that for the helix, especially, we do not yet know the ideal mixing frequency. And then also, of course, the question will remain open, even though we can reduce half of the amplitude. What does this platform motion have for implication on the loading of our entire floating offshore wind turbine system? And then quickly, actually, I'm slightly over time, but quickly to wrap up this presentation. So what we're ultimately working towards is, let us say we have knowledge on what kind of frequency we need to achieve wake mixing. Is there a way that we can design our platform such that it excites exactly these frequencies with very minimal pulse or helix input, so that we need minimal control action to achieve a maximum amount of wake mixing? With that minimal control action, because we have some headroom left over in our controller, is it also possible to do maybe load minimization or even combine the three? And this is something we are hoping to work towards in the upcoming years. And with that, I would like to end my presentation. And if there are any questions, I'm happy to answer them now.
Thanks a lot, Daniel. Very nice presentation. I think maybe you can stop sharing your screen for now, and then we can see maybe all the speakers of the short presentations, so we can have a little bit of a panel discussion. I don't see yet any questions on the Q&A, so please do post them in your Q&A tab so that we can address them now. I have maybe a general question. We heard a few times today about the possibility that floating wind offers to dynamically reposition the turbine. How, maybe that's a question for multiple speakers, how do you see this really realistic or feasible? Do you have any thoughts on that? I don't know who wants to start. Maybe Daniel, we see you. I don't know if you have any comments on this.
So it's yeah, for me it's very so like wake mixing itself, it hasn't been applied on a wind farm as of yet. So but I do think that because the way the interaction is with a floating offshore with a floating turbine, because we can reduce the pitching angles or maybe even lower frequency, so we can reduce the loading in that sense. There's potential that might come quicker than we expect.
Right.
But it's still very much future work. So
yeah, sure. Anyone else want to comment on this?
I think I'll agree with Daniel that seemed to be something which needs quite a lot of a bit more research to advance. Conceptually, because floating turbines float, conceptually they can move, but there's not enough research in that area at the moment. So that'd be something that we needs a bit more research in the future.
Yeah.
May I add something to it as well, which might be interesting? It's, I think what we're looking at, for example, with this co-design of platform design is, so nowadays controls are generally, control systems are generally added to an existing mechanical design and to improve it. However, we're actually taking a step backwards and say, okay, how would you change your mechanical design if you include controls in the overall process? This is this co-design idea. And that's, I think, has a lot of potential because then you might find ways to mitigate these pitch bearing, specifically, for example, loading problems. So it's like you have to redesign the entire system to increase the overall performance, whereas now you're just putting stuff on top of it.
Right. Yeah. Thanks a lot. We have a few questions that came in. So one is about the helix. I think this is for you, Daniel. In terms of loading, doesn't helix create, in a way, a partial wake situation for the turbines downwind?
Yeah, so we do not know yet for sure yet. So that's like right now what we're looking into is trying to find a proper explanation also for the pulse as to why do we see such a significant increase in wake mixing or average wind velocity. Maybe that's a better way to put it. And we think specifically for the helix that because we have such relatively high yaw angles, it's actually the wake steering or wake deflection that we're doing that's causing the most, is giving us the most gain as of now. So I think that answers the question. Yes, thank you.
We have another question from Craig. He's asking, how would the wake mixing method be applied to tension leg platforms such as TLP? Is it impossible for such a platform?
I think it's also a question for me. Mm-hmm. Yeah, so this is again also something we assume is that the platform is free to move, and what we've seen in other research with also tension, I think tension platforms, that they can move in a certain area around the sims. It's actually quite significant. So based on that, we said, okay, well, these pitching angles, they are present, but they're also not that big that you would say you're reaching the limits of what the system can do. But it's again, this coupling to the real world is as of yet missing.
Maybe I have a follow-up question related for Javier on this. So you showed, Javier, of course, the impact that the floating turbine has on the design of a controller. Is that somewhat less critical, I guess, maybe for a TLP, which is less dynamic? Or can you maybe comment a little bit on that?
Yeah, TLP, it's like a fixed turbine. We can try to have the same controller there.
Okay, so a normal controller usually can do the job for a TLP.
Yeah.
Okay, yeah, good to know. Thanks. Then there is a general question for, I think, all the speakers. Do you have any detailed information on how the differences in control systems affected the production of the turbines? So are we talking about differences in millions of euros or pounds, maybe, or in generation per year, or much less? Does anyone have thoughts on that? Tricky question.
I guess it depends what you define as control systems. There are quite a few different types of control. Certainly, if you start talking about the electrical side, it can make a difference across the wind farm of millions or relatively small changes. If you start to include different ancillary services, for example, it can be quite a lucrative additional channel to power production. So that can make quite a significant difference to the wind farms or wind power plants' total revenue over its lifetime without causing any significant difference to the asset lifetime.
Okay, great. Thanks. We have another question. Is it possible to include in the platform devices similar to those that are used in buildings for earthquakes? I'm not sure I understand the question. So it is possible to include in the platform devices similar to those that are used in buildings for earthquakes or vessels for reducing seasickness. I'm not sure I fully understand the question. I don't know if anyone wants to react, or maybe we can ask the the attendee to maybe clarify.
I think the question is, it is possible to include in the platform devices such as those used in buildings for earthquakes or vessels in order to reduce seasickness.
Right.
Yeah, you can use variable ballast to control the platform in such a way similar to the use in buildings for earthquakes with the seawater.
Right, I see. No, yeah. Thanks, Pranav.
Is that technique still already in use, or do people already use it in these platforms? The one you're talking about, Javier?
About the Nautilus
The ballast. Yeah.
Of Life 50 Plus project. It's an open model. You can check it.
Great, thank you.
Nice. Then we have one last question, as far as I can see in the Q&A for now, a quite interesting one. So if you install one control system during the design of the turbine, but years later you realize there are better control systems, can it be changed? Is it easy to reprogram the turbine, essentially? Anyone? Yeah, Michael?
I
think.
Sorry.
Go ahead.
I was going to say, in theory, yes, it's relatively straightforward. But the wind turbines are normally still owned and managed by the wind turbine manufacturer. So if the wind turbine manufacturer wants to change the control system or update it, then it's probably relatively easy for them. For a third party to do, it would essentially involve probably destroying the warranty with the wind turbine manufacturer, which cause some issues for the wind farm operator. But it depends on the structure that they've got. It's more legal than technical, I think.
Anything to add, Ampea, on this? Or?
Yeah, so just to add to what Michael said, so is it possible to do it? Yes, but there are some challenges. So if you're looking at specifically wind turbine control, usually the controllers are potentially flexible so that they can be adapted. But if you want to change the whole control system, it is possible, but it's still challenging. Not it includes perhaps not changing specifically just that controller, but other PLCs along the turbine. So it's more complicated than just reinstalling a controller.
Yeah, understood. Clear. Thanks. Last question, Ampea, are you aware of any studies investigating the impact on the anchors and moorings of inducing cyclic or repetitive movement in the floating platform?
No. It is one of the things that we, again, in the future have to look at. What does it mean for our actual platform?
Yeah, so it seems there are some fruits for further research in that area, indeed, to look at the whole system and its impact on the anchors and moorings as well. I don't see any more questions, so I think we can slowly close the session for this morning. I'd like to thank again all the speakers of this morning for the very nice presentations. It was very informative. And I invite everyone to join back at 2 p.m. Central European time, where we will have a session dedicated to energy storage and hydrogen. So thanks a lot, everyone, and see you later. Bye.
Thank you.